Hello students, let's begin at the very high energy end of the spectrum, gamma rays. These rays are like the powerhouses of the electromagnetic world with wavelengths less than zero point 0.1 angstrom or 0.01 nanometers. Where do they come from? Mostly from inside the nucleus of atoms during radioactive decay. That's why we say their origin is nuclear. But not just Earth, cosmic rays bombarding us from outer space also carry gamma radiation. So in a way, the universe itself is constantly whispering gamma rays towards us. Now, what makes gamma rays special? First, their penetration power is astonishing. They can pass through even 30 centimeters of solid iron. That's like light passing through your classroom wall. They also cause fluorescence when they strike certain materials like zinc sulfide. But here's the catch. Their immense energy can damage living tissues, which makes them dangerous without protection. So how do we use them? In medicine, they're heroes. Gamma rays are used in radiotherapy to kill cancer cells. In industry, they check welding joints and detect faults inside metal structures. The same power that makes them risky also makes them incredibly useful. Let's now slide down to X-rays. Unlike gamma rays, their origin is not nuclear but electronic. When fast-moving cathode rays crash into a heavy metal target like tungsten, the sudden deceleration produces X-rays. Their wavelength stretches from 0.1 angstrom up to 100 angstroms. That's longer than gamma rays but still far shorter than visible light. You can think of them as the middle children between gamma rays and UV dot. X-rays are more chemically active than ultraviolet rays and they leave their mark on photographic plates. Like gamma rays, they also produce fluorescence in crystals such as zinc sulfide. Now, here's the interesting part. They can pass through flesh but are blocked by bones. That's why doctors use them for radiography, spotting fractures in bones or even dental cavities. Beyond hospitals, X-rays are detectives in science labs. They reveal atomic arrangements in crystals and even help geologists study precious metals hidden deep underground. From CAT scans to crystallography, X-rays are everywhere. Let's move one step closer to the visible region, ultraviolet radiations or UV rays. Their wavelength is just shorter than violet light. Where do they come from? Electric arcs and sparks produce UV. Mercury vapor lamps emit UV along with visible light. And of course, the sun is a massive UV source, though thankfully, most harmful UV is absorbed by the ozone layer. To study UV, we can't use glass prisms because glass absorbs it. Instead, we use quartz prisms which let UV through. So, what are the traits of UV? They travel in straight lines with the same speed as visible light, 3 times 10 to the power 8 meters per second in vacuum. Chemically, UV is very active. It can trigger reactions in dyes, photographic plates, and even skin cells, which is why too much exposure causes sunburn. But UV is not all bad news. In fact, it's quite useful. It helps sterilize surgical equipment, it enables the skin to produce vitamin D, and UV lamps are used to detect fake currency. Forensic scientists also use it to reveal hidden clues in crime scenes. So, UV is like a strict teacher, harmful if overexposed, but extremely helpful when used wisely.
Let's tie it all together. Gamma rays, X-rays, and UV radiations are all invisible parts of the electromagnetic spectrum. Gamma rays, nuclear origin, highest energy, deepest penetration, medical and industrial use. X-rays, electronic origin, medium penetration, imaging and crystallography. Ultraviolet, just beyond violet, quartz required for detection, chemically active with applications from sterilization to forensic science. Each radiation is unique, with its own dangers and benefits, but together they show how powerful and versatile the electromagnetic spectrum really is. And that's the wonder of physics. Invisible waves shaping our visible world. See you in the next lesson.